Hi, in this video we're going to be talking about solving non-homogeneous linear difference equations. So to start out with, I want to review some stuff from last term. So recall that if we have some line going through these two vectors that I have here, notice that this line is not a subspace of R2. In particular, this purple line here, L, does not go through the origin. So we can take this line L and translate it so that it actually does lie on the origin and get this line L prime. Okay, so L prime is a subspace. L prime goes through the origin. And there is a nice relationship between vectors in L and vectors in L prime. And so that relationship looks something like this. So a vector L is on the line L exactly if, when we take it and then shift down here, we get to something on the line L prime. Okay, so how do we shift down? Well, we just have to take this vector that's going from the origin up to L and subtract that off. Okay, so in other words, if we take any point on the line L and we subtract off this vector u, so I'm adding the vector negative u, it's opposite of this vector u here, then the point that we get to will lie on the line L prime, necessarily. Okay? Well, there was nothing special about using u there. We could have also used this other vector v. So it's also true that if L lies on the line L, then L minus v lies on the line L prime. Okay? So I can start out with any vector on this line. Let me just draw this here real quick. So I can draw negative v and get back to the line L. Okay, so we can start at any point on the line L and subtract off either u or v to get to L prime, and similarly we can start at any point on the line L prime and add u or v to get to a point on the line L. Okay, so I want to take advantage of this fact. So I have this vector here drawn, w. It's lying on the line L. And because L is a subspace, it's a one-dimensional subspace, the set of all points on L, L prime, look like this. We take some constant times the vector w. So L prime is just this set of scaled versions of w. Okay? So w you can get from doing v minus u in this case. That won't be relevant for what we're doing, but we do need to know some way to span the line L prime. Okay? So if we know this is the set of vectors for L prime, then we can come up with a set of vectors for L. L is the set of vectors which, after adding u to them, L is a set of vectors which, after subtracting u from them, we get to something like this. So we just need to take something like this and add u to that. Okay. We could have also done the same thing for v. Okay. One thing to note is that if we have a particular c giving us some point over here, and we wanted to look at the same point over here, we would have to have a different value of c. But still, if we run over the set of all real numbers for c, that's going to be the same as the set of all real numbers for c over here. We get the same set of vectors out, which is the line L. Okay, so this is the one-dimensional case sitting in R2. We can also look at, over here, the two-dimensional case in R3. Okay, so we're going to look at this plane, this purple plane, that's not a subspace because it doesn't go through the origin. And we want to consider what happens if we shift it back down to the origin. So we have some plane sitting out there that's not touching the origin, and we want to shift it back, and the way to shift it back is to subtract z from it. So there is a vector from the origin out to the purple plane, which is z. Okay? We also have these two vectors x and y, which are linearly independent and span this plane p prime. Okay? So very similar to this, we can say that a vector p is in this purple plane p if and only if p minus z is on the green plane p prime. Okay? Well, we can describe the vectors in p prime by saying that they are all linear combinations of x and y. So p prime is just the set of linear combinations of x and y, and therefore p is just z plus those linear combinations. So when we're looking at solving non-homogeneous linear difference equations, we're going to run into a very similar circumstance. Our solution set will not be a subspace, but it will be some shifted subspace. Okay? And then we can find out the corresponding p prime, the actual subspace that corresponds to it, by looking at the corresponding homogeneous case. And then as long as we can find one point that's actually on our solution space, and we have independent solutions to the homogeneous case, we can write all solutions to the non-homogeneous case in the same manner. Suppose now that we have two solutions, Zn and Bn, to this non-homogeneous linear difference equation. Okay, now I want to say that if I subtract those two, I get a solution to the corresponding homogeneous linear difference equation, which is the exact same left-hand side of the equation, but the right-hand side, instead of f of n, we just have 0. All right? So the reason for this, the reason why this difference must be a solution to the homogeneous case, is because if I plug in the difference, so bn minus zn is the nth term, all the way up through bnk minus znk is the n minus kth term, then I can distribute the lambdas in, and then group all the bi's to the left, all the zi's to the right, and the first bracket here must be equal to f of n, because bn is a solution to this stuff equals f of n. That's exactly saying that this stuff is equal to f of n. Okay, also zn is a solution, so the stuff we have in the right bracket is also equal to f of n, and we're subtracting the two things, therefore we get 0. Okay, so the difference of any two non-homogeneous solutions is going to be a corresponding homogeneous solution. Okay, very similarly, if we have xn is a solution to the homogeneous case, and we add it to zn, which is still this zn over here, a solution to the non-homogeneous case, then we can do the exact same argument of plugging in the sum for xn plus zn, and we end up with a bracket plus bracket. One of them will be 0, the other one will be f of n, therefore we get 0 plus f of n is f of n, and this sum is another solution to the non-homogeneous case. Alright, so I'm trying to relate this to what we just saw before with the lines and the planes. So if we say that n is the set of non-homogeneous linear difference equation solutions, and h is the set of corresponding homogeneous solutions, then what we just said here is that Bn is in n exactly when Bn minus Zn is in h. Okay? The two directions of this implication are these two statements here. Alright? So for the exact same reasoning as before, we can take some particular element of n in that shifted plane, add it to some vector in the actual subspace coming from the homogeneous case, and we get an arbitrary vector in the shifted case. Okay? So the way that we're going to express the solution set of n is to find one particular vector in n and then add it to our general solution for the homogeneous case. Alright, we already know how to describe these xn's here. That's just the last video. And now we need to just be given some Zn in n in order for this to work. Now there are ways of guessing Zn's, and this is just something that I'm not going to go into. It's beyond the scope of this course. So we're going to avoid that. For these problems, I'm going to give you some Zn, and I just want you to know what to do with it. So let's go through an example. Here's an example of a question you might see coming in two parts. The first part asks you to verify that a particular solution actually works. Okay? And then the second part will be finding the general solution. Okay? So I'm going to use something very similar to the problem we saw yesterday. This we already know the solutions of, and we'll take advantage of that later, because that is part of the problem to solve the homogeneous case. So our goal right now is to verify that this sequence, the sequence defined by this equation, satisfies this LDE. Okay? So to satisfy an LDE, I need to say that for n bigger than or equal to k, in this case k is equal to 2, second order, Zn minus 4Zn minus 1 minus 4Zn minus 2. So that's the left-hand side. Hopefully it's equal to the right-hand side. So let's see what it actually is equal to. So Zn is this. Okay, minus 4 times this with an n minus 1 plugged in. So I'm going to take a shortcut here. I'm subtracting this off, and I have a minus sign here. I'm just going to make that a plus. And if I replace n by n minus 1, because we're looking at the n minus first term, then this n plus 6 is just going to turn into an n plus 5. Okay, so we have plus 4 times n plus 5. Okay, similarly I want to replace this n with n minus 1. And so n plus 1 just turns into n. Okay, something similar is going to go on here. We have a minus sign, but this also has a minus sign, so I'm going to write a plus. It's going to be 4 times, replacing n by n minus 2 here, is going to give us n plus 4. And finally, n plus 1, where the n is replaced by n minus 2, is going to give us and minus 1. Alright, so this is a little bit messy. We're just going to try to clean it up. So to start out with, I'm going to group the 4's together. So I have 4 times 4 to the n here, and that's just 4 to the n plus 1. I'm going to do something similar here in this last term. 4 times 4 to the n minus 1 is just 4 to the n. Alright, so I now have 4 to some stuff in each of these terms. I'm going to factor that out. So it looks like there's n plus 1, and n. So I'm going to take the smallest one, 4 to the n, and factor that many 4's out. Okay, so what is left? Well, here we have negative 1 4 left, and then a factor of n plus 6. Okay, here we also have 1 4 left. And we have an n plus 5. And here we pulled out all the 4's, so we just have n plus 4. Alright, so we pulled out this 4 to the n. We're trying to verify that this is equal to n times 4 to the n. So here's our factor of 4 to the n. Hopefully this parentheses here is equal to n. And if you go through this, hopefully we can just see this without writing anything down. Let's look at the constant term first. Here I have minus 4 times 6, that's negative 24. Here I have 4 times 5, that's positive 20. And here's positive 4. So that's positive 20, positive 4, that's positive 24, and that's going to cancel out with our negative 24. Okay, how many n's do we have now? We have negative 4n coming from this. We have positive 4n coming from that. Those two cancel each other out. And there's 1 n left over. So indeed, this parentheses here is equal to n, because everything else cancels. So this is n times 4 to the n. So this is now verified. Okay, so we're now going to write down the general solution, and the key is to use the fact that we already have one specific solution. Okay, we also have, if you recall, this general solution to the homogeneous case. So replacing this n times 4 to the n with 0, we get this, and this is the problem we solved yesterday. Here was the solution. Okay, so we're going to use that solution along with our specific solution to the non-homogeneous case and just add them together, and that will be our general solution to the non-homogeneous case. And that is the answer. So all of the special cases that we had for the homogeneous cases still apply here. Those are all based off of what's going on the left-hand side. What's going on the right-hand side is going to heavily affect this specific solution, but you don't have to worry about finding that. You just have to worry about verifying it once I give it to you. All right, thank you for watching.